Right. So, yesterday I was talking about the weather. And did a little brainstorm of some of the stuff that we're going to study about heat. And we talked about temperature scales. And I happened to find this highly useless thermometer that separates from the scale. So here I've got my liquid in glass. That will be methanol, coloured methanol, not drinkable. And all I got to do is put it somewhere where I know there is zero. So there's a balance between ice and water. And then wherever the level is, I mark that and glue this in and hope that it's in the right place. Or I could check all the other thermometers and see what the temperature in the room is. And if it was like 22 degrees, I'd put the top of the blue line at 22 degrees. So by doing that, I would hopefully be calibrating my thermometer in the scale with it. Okay, I have something to show you. This is where I realise I forgot to get matches. That's what matches, keys, brain. Brain, where is my brain? So, gather yourselves around the front. Okay, I'm a bit cautious of them now after nearly setting fire to myself a while ago. So, there I have a flame.
Wait, it still has some.
Yeah. Better? Okay, and here I have a metallic strip that I have heated up before so it doesn't look all nice and shiny. Okay? Here I have my device where I am preventing my fingers from being burnt. So I'm going to hold this in the flame. What is happening to it? It's bending. Why? Heat. Explain a little bit more. Like, here I have an alternative holding device that I'm holding in the flame. Is it doing anything? It takes a shorter time to heat up. Okay, you want me to stand here for half an hour?
Yes. And this has like lower melting point.
No, thicker and thinner.
Yeah.
Thicker? Thinner? So this is bending because it's a thin piece of metal. Yeah?
Yeah. The type
The type of metal it is. What's happening now to it?
It's getting hard.
It's hardening. Just happening to it. Softening. Cool it down. Wait. Wait. What?
Bendy. What has got on?
Hey, it's bending it now. So what is this? Just put it in the water now.
Put it in water.
No, it's just bending. It's a little That's the
Should make a science based measure.
Well, it's bend in both directions.
Spinning on only one.
Yeah, but
Okay.
is it always bend in the same direction?
Short bit of the peg to the top. Okay, which way is it bending?
Down.
Downwards. Short bit of the peg to the bottom. Which way is it going to bend? Okay, so what have you deduced about it now? When it's heated, it will always bend in the same direction. Why? What's going on? Is it at all useful?
It exists.
It has to be useful.
It exists.
That's a very interesting philosophical argument. It exists, it has to be useful. Mosquitoes. Actually, they're quite an important part of the food chain. Okay.
Yeah. Actually.
So, it's a metal strip. It is to do with what it's made from. It's actually not one metal. It's two. Two different metals rolled together to make it look like one sheet.
So it has like this stuff.
Copper.
Probably copper on one side, probably iron on the other. So it's got two layers sandwiched together. How is this useful? It's got a property that changes with temperature, like volume changes with temperature here. So if you have this strip, which is called a bimetallic strip, and you put it in an environment where the temperature is going to change, you can turn this into a thermometer. If you look at your sauna thermometers, you will probably find that there is a metal coil at the back of them. That metal coil is one of these strips rolled up. Because the hotter the sauna will get, the more the coil will stretch out and the more the needle on the thermometer will move around. It's an easy, non-poisonous way of making a thermometer. So it is relying on the expansion of a material in the same way that the liquid in glass thermometer relies on the expansion of the material. Okay. One more thermometer, which hopefully I won't break on the way through.
But it's over. Tune's white.
Apparently the daddy of all thermometers, because Galileo invented it. It's not very accurate. They've probably got a very big one in Diethelmar. Okay. But how does it work? What temperature is it reading at the moment?
25.
It's at the top.
It's at the top, yeah. Or 19 at the bottom. Is there anything happening to it? I can see something happening to it. What's, have you noticed anything?
The colors are going up. And the colors at the bottom are going up.
The colours at the bottom are going
They
up,
have
aren't they?
the glass. The glass. Inside. Glass wall.
No, not that detail. It's been in a cool room. I just want to provide some heat nearby. You should be able to see it now.
The water's going up.
The water's going up,
Yeah.
maybe. You need really good eyes to see that. Am I just hallucinating it? Is anything happening to how far apart the balls
Yeah,
are?
We're spreading.
Yeah.
They're spreading.
I'm thinking of them.
What's happening to the blue one?
It's going on the left.
It's going, blue one, it's going down.
The mouth's going up.
Yeah? Now it's going up, is it?
No, but it looks like it's gone up a little bit.
Okay. This is a very, very slow acting thermometer. My guess, the temperature in the room, believe it or not, is somewhere around 21 degrees Celsius. It's just been in a cooler storeroom. And that cooler storeroom might be at about 18, 19. Now, this is sinking down. As the temperature evens out, as this whole thing heats up, and let's say it's going to become 21 degrees Celsius, this will sink and 21 will be at the bottom. If the room was at 23, this would be the bottom one. These two guys would sink down, or girls. Gender non-specific glass objects, the guys would go. So you can be sort of accurate to 2 degrees Celsius. If you made a much, much, much bigger one, you could have 20.1, 20.2 on each of those discs. So how does it work, or why does it work?
Do they have some numbers on it, Chris?
Yeah, sorry, they do. These little discs, that's got 19, that's 21, that's 23, that's 25. So this one, which wasn't very expensive, it's designed to work at room temperature. So if you came into a room and the blue one was at the bottom, it would be cold. If you put this in your sauna, they should all be at the bottom.
Can they go past each other, or will they?
No, they can't. They're too big to go past each other. But in theory, they shouldn't necessarily have to go past each other. It's not fantastically accurate, but it's a lot more accurate than this one. But well, how does it work? It's got to work with a property that changes with temperature, and it's very, very fine-tuned. Yeah,
Do they have like different liquids inside the glass?
they might have.
Or are they just dry?
They may well have different liquids, but chances are they have got they're the same liquid with a dye in it. But what you've got is a liquid and then you've got air. But there is something different about each of these units.
The ratio of constants, or like the difference there, is it different?
Yeah, leading to not quite a volume change, but
Pressure? Weight?
yeah, the density changes because their weights are slightly different. Their volumes might also be slightly different, but actually it's their density that is crucial. So then what will happen as it gets cooler, this is contracting. So it's getting smaller, its volume is decreasing, but its weight hasn't changed. So therefore its density is increasing and it's sinking. Really neat idea. And the accuracy you've got to have to make it, because we're talking about fractions of a gram, fractions of a cubic millimeter differences in volume. So it's a nice little gadget, and you can buy much bigger ones with all sorts of different coloured thingies in them. Not the world's most accurate one, but it's not bad. I must admit, I've used it. I used to have it up on the window there. I'd come in and think, why are they all at the top? There is no way they should all be at the top. You shouldn't be working at a temperature at 19 degrees Celsius. And there is a leak around that particular window, which I've tried to plug up. We can leave it like that. We'll leave it there for the moment.
Karen,
Yeah.
can you explain again, why did they go down? Because I didn't get that.
Didn't you? But that was so easy. There is something, a property must change with temperature. Yeah. If it's sinking, it is because it is heavier than those. Yeah, this is less buoyant. If they've all got the same weight, the same mass, then actually their weight can't change.
Yeah, that's what I'm coming.
But their volume can. Yeah, so the size of what is held in. So actually their density changes. Because whether you float or sink depends on your density. How much material you've got in size. Yeah, so for instance, you could have, this will float if I put it in water. But if I make that same mass into a mass of metal into one solid lump and take the air out the side, it's got the same mass, but it will sink. So actually it's the density. So the property that changes, like in many thermometers, is the volume, but the mass stays the same. So the volume is decreasing, density increases, this drops down. Okay, and basically it works that the temperature should be between 19 and 20 and 21, because that's a 19 on there, it's a 21 on there, so it should be at 20 where that thermometer is at the moment. Neat. Pretty. And not at all electronic, which is also something that is to be valued. So, what's the property here? Well, it is volume that changes, but it is also, it leads to a change in length. So, when I heat this up and it bends, one side of the bend, the outside, is longer than the inside. So I've got two metals that are mashed together, compressed together. I heat them up, and one metal, it wants to expand more than the other because they're not identical. And the only way it can do that without separating from the other metal is to form the outside of a curve, which is longer. Neat. Very neat. If I heated it up enough, it would rupture apart. Okay. Yes, I think it would rupture apart. Well, but maybe I'll get to the melting point before then. I certainly couldn't do it with that. So there we've got the expansion being useful. We're putting it to good use. Many, 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 many times it is not useful. And we don't want it. Okay. So for instance, what if you've got a building which has got a steel structure, steel frame, and you put loads of concrete around it, and then it heats up or it cools down? How do you know that your concrete is going to expand at the same rate as the steel and not kind of do the curvy thing here? And that leads to all sorts of engineering and building problems. Steel places. So, have you ever noticed, have any of you ever noticed where buildings have been crumbling or rocks have been crumbling and somebody's said to you, oh, that's because of the change of temperature? That damage has been caused by change of temperature. Yeah? Where?
Wasn't, I think there was a building that,
Here.
no, I think it was a while back.
Uh-huh.
I'm not too sure where it was, but I do think I heard about it because my dad works in the
Yeah.
Asphalt, like on the roads.
Tell me more.
Well, what do you mean anymore? They said that like when it gets like hotter,
Yeah.
yeah,
You don't have to write this at the
then
moment, yeah.
like the ground expands and then the rocks like have to go with it.
Yeah.
No, they can't.
You've got the road surface here, and then you've got the rocks. If you have got a very, very big temperature change, say from summer through to winter, in winter, these rocks can occupy a smaller volume compared to the road volume than they do in summer. And you can actually get lots of cracks in roads. Uncovered.
That where like the sidewalks where I live, they have cracks in them. Like yeah, like that. Yeah.
In the US.
Yeah, they have cracks like when they expand, they don't go like this. They
Yeah.
kind of just go closer together.
Yeah.
They don't like.
They have to fix it like, at least in my neighborhood, they fix it like every spring. Like all the tiles that are cracked, they take them off.
Wow, they actually fixed the tiles. Yeah. No, that's good.
Yeah.
They do. Yeah. In the UK, generally there would be blocks of asphalt, and there would be tar between them. And in winter, there would be more of an expansion gap. And in summer, this would decrease it. You get a little ridge of asphalt that actually in winter would dip down here, because asphalt or tar is a very, very slow moving liquid. And you could just go over it with a roller and it will push it back into place. Yeah, that's why. I've got to admit, I'm absolutely stunned that I still can't quite work out why, but you don't see that here. Yeah. But there are other problems that we've got, because we've got a much bigger temperature range than maybe you had where you were. There's also a problem if you've got a climate that stays around 0 degrees C a lot. So you've got many nights that dip below 0, but the day goes above 0, because some countries can have months of that. That's a slightly different problem, but it does lead to problems within, it's got a slightly different effect, but it does lead to problems within buildings. Yeah, so actually what we've got in Finland is a massive difference in temperature between summer and winter. So let's say that we've got Oulu here and Helsinki here. It's possible you've done this in maths, believe it or not. And we've got a railway line connecting the two. How many kilometres is that railway line? About. Let's assume it goes directly. Oulu, Helsinki? 600? 600 kilometres. Yeah? Now, in winter, coldest day, -30. Hottest day, +30. That's a 60 degrees Celsius range of temperature. That is going to have an effect on the length of railway line. Yeah.
It's gonna become longer
When?
when it like goes hotter.
Yeah. In summer, the distance from where you stand on the platform in Oulu, measured along the rail, to where you would get off the train onto the platform in Helsinki, is going to be longer.
How much longer?
Okay, let's work it out. How do we work it out? There is a formula. You can just watch at the moment. Change in length is equal to the original length times the magic number alpha times the temperature change. That would make sense. If you've got a big long length to begin with, it's going to change in length by more than if you had a little tiny length. Does that sound reasonable? Yeah. It's gonna, was that a no?
Yes.
So yes.
No, yes, no.
Yes, no, 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 yes. But so if you have a huge great length of it, you heat it up, you're going to notice the difference much more than if you had a tiny length of it. If you heat it up a load compared to 2 or 3 degrees Celsius, you're going to get more of a change. So that's going to be 600 in kilometres times this magic number alpha times the temperature change, which is 60 degrees Celsius. What is our magic number alpha? Our magic number alpha, which I've got to look up, depends on the material that the rail is made of. It's called the linear coefficient of expansivity, alpha. And alpha is different for every material. So for instance, for copper, it's different compared to steel, which is why that strip bent. Now, the railway, our rautatie, is made out of rauta. And for iron, that is 0.000012. Okay, so we have 600 times 0.1234 times 60 in kilometres.
I missed that 0.
Did I?
After the
Thank you
decimal.
very much. Now, I did say no calculators, didn't I? No calculators this year. Now I'm beginning to regret this. Right, what have we got? 2 zeros after the decimal. Sorry, before the decimal. 2 zeros after. 1 0 before, 1 0 after. So they cancel out. So I've got 6 times 0.012 times 6. So 6 is a 36. 6 times 0.012. So how do I do that? I do 36 times 2 times. I've had to multiply that by 1, 2, 3, 4. 0.0004. 36 times 12 is what? 300 plus 70. 3, hang on. 300. Is it? This is 372.
Oh, wait, never mind.
Sorry, that's 1. 400 times 1, 2, 3. Okay, it is 432 meters longer.
Yeah, that's not just like half kilometers.
Yeah, nearly half a kilometre. That's about right. I've done it before. I know that's about right. Don't worry about how I did the maths. You might have your own way of doing those multiplications. So in summer, the rail is half a kilometre. The railway is half a kilometre longer than it is in winter. Now, most people are thinking, well, what happens to that extra half a kilometre?
How do they like work around that? Because when they built the railroad, they would have to like notice in advance.
Yeah. It's not just the railroad, it's all the cables as well. Yeah. You don't make it out of one piece of rail. If you do, you've got a bit of a problem. You will get stuff like that happening. You can't stop the force of expansion. So actually what will happen is the rails bend.
Why would someone make it out of one like rail?
Because they're stupid. Now, that is a highly, highly unusual situation. You will not get this over a year. You would get some sort of damage to the rails looking like that. That's a little bit extreme. You will get some sort of damage to the rails if you've had a really, really hot day. The transport network of Britain is not designed to run above 30 degrees Celsius. That's not that unusual a temperature. Okay, it's unusual here, but it's not designed to run because basically the trains don't fit on the rails and the rails start to bow. So with climate change, areas that are getting hotter, things like the infrastructure of railways are having to be dealt with. How do you do it? Well, you have separate sections of railway. This is a not very good way to do it. Okay, you have separate sections of railway. One bit of rail here, one bit of rail there. These bolts might be loose, but not so loose that they're going to fall off, or that is dangerous. And these will expand into each other, a bit like the asphalt and in the road, that they can move in together. But if the gap is so small on a very, very hot day, it disappears, then those rails are going to move. You know, they're going to bow out. And my guess is, where's it gone? That's an expansion. Actually, let's copy it into here. This repeating bowing pattern. This is an expansion point, expansion gap that couldn't expand anymore. This is an expansion gap, etc., etc. And if they'd made them a little bit bigger, then those rails wouldn't have had to curve out. They're fixed somehow to the sleepers here, so that's why they're both going one way. Otherwise, one could go out like that, and the other could go out like that. Not good. If you've got a very limited temperature range, that will work. Another way to do it, because this actually is quite dangerous, if this in winter gets to be so big, like that amount of expansion gap, when your wheel goes over it, the wheel might sink into it briefly. Not good. Rough train ride. So most railways actually have something that is tapered, which is clever, because if we're looking at it from above, the train wheel goes over it, contacting there and there. It's never not contacting a piece of iron, and that makes a much smoother ride. Yeah, so that's for like a daily change of temperature. If you've got something like Oulu to Helsinki, then that temperature change is gradual. Though I must admit, there may well have been problems recently when we've had -20 one day and 2 degrees the next day, with a big temperature range. So what we've got over the year is that actually the whole ground is expanding and contracting at the same rate. So it's not like the rail juts out 1/2 a kilometre at the end compared to earlier. Put your phone away. Thank you, just noticed it. Annika's fault for turning around. The whole ground is also expanding. But what if it's not attached to the ground? What if it's the cables? Have you ever noticed that power line cables? So here we have one pylon, let's say. Here we have another pylon. In summer, the cables are like that. In winter, they're like that. So they sag more in summer. In winter, there must be huge problems with it, because you've got a much more contracted distance, and you've also got possibly a weight of snow or ice on them sometimes. Actually, again, that problem would just be around 0, because it would just be ice. You don't get so much ice when it's -30, I suppose, yeah. So these problems have to be taken into account. If you are changing material, like you are using concrete and iron, you do have also a bit of a problem. It's easier to shape metals, and this sort of arrangement is very useful on bridges. So my bet is somewhere on Rautasilta, at least you've got an arrangement like that. That is a very, very common arrangement.
What is that?
Isn't it obvious? Sorry, I'm glad you asked these things because I think, right, here you've got a road surface, there you've got a road surface, and here you've got an iron plate. So those iron fingers, when it gets cooler, they will contract, but you never lose contact. So if you were walking over that, you wouldn't fall through a hole. And then there's room for them to expand in summer. Not very much, I'd say that's on a hot day. So if you've got the bridge going over the Oulayoki, you've got the deck of the bridge, and that's somehow got to be attached to the road on the other side. And usually it's movable somehow, because if you've got something that is a very, very fixed structure, as soon as you get temperature problems or if the materials aren't matched, then you get expansion problems, and it can crack concrete. You can't resist the power of expansion. Yeah.
What about the bridges that like do this and then they can open up to let like a boat in?
Yeah.
So if they're like close together like this in the summer, wouldn't like and they're like this in the winter, wouldn't there be like a problem
Yeah.
if someone falls through?
Hopefully not that much of a problem. So what they would probably do, if it was likely to be a problem, is that the very tips would be tapered together so that they could rest over like that, or it could be fingering together like that. Usually you're only talking about centimetres, usually. But the whole problem with the railway line from Helsinki to Oulu, it's a fun one. There isn't a problem because it's been designed and built so that there aren't so many issues around it. It's clearly been designed very well, and in fact, they cheat a little bit with weights on the cables, tensioning weights on the cables, so that on a very, very, very hot day, you wouldn't have the cables hanging too far down. Because again, the cables have got to be at the right height for the train. I can't remember what it's called, the pantograph, I think it's called, that it picks up the wire and the current flows through the train, so the train will actually work. Pretty amazing technology that is needed. You might find that on very cold days, motorised equipment doesn't work anyway because the bits don't fit together. So for instance, diesel engines don't work below minus 35 degrees Celsius, is it? We don't usually get a problem in Oulu, but I remember Helly saying she grew up in Kuchma and she just said, oh yeah, minus 40, no school, because the buses don't work. That's the only reason that there was no school, because you couldn't actually physically get there in time. So diesel engines don't work below minus 35, I think it is. And
why you don't see any trucks here, like board trucks. You know,
huge, great trucks.
like pickup trucks. Most of a lot of those are diesel.
You see pickup trucks,
Yeah, like a truck when it has like
flatbeds.
yeah, bed in the back.
Yeah, they do exist. One
Well,
rescued me once when I
I
broke
don't
down.
see like any of them here.
Okay.
Well, when I see them, they're like
Yeah.
rarely ever.
Yeah, they are. Actually, to be honest, a lot of the trucks here are set up so that they don't break down.
Oh yeah.
Very good. And if you have minus 50 Celsius, like in Siberia, you simply don't turn the engine off once you've got it going. So diesel engines will work, trucks will work, because the engines are left running overnight in garages. That's how it works in even colder climates. I know, what a waste that is, the carbon dioxide. But then again, if you live in a place that does regularly drop down to minus 50 every winter, then you've got to do that. Any questions? Have I been going longer than 45 minutes? Yeah, you need a stretch break, don't you? 3-minute stretch break. Then we're going to do some sums. That must be a very old doodle.
Not mine.
It's all right. Doesn't matter. Doesn't matter.
No, it really isn't. No.
Only that's not how you spell hoe. That sort of hoe, even if it has got a different meaning, is where you go in the the garden. Yeah.
No one wants to go.
Hey guys, I've just sent a message to all your teachers that if you have a 90-minute lesson, can they please give you a stretch break? Because you like it so much.
What is these? I would like to add the other day, so now my hand. It looks like something you put inside one next to
I thought that this was I checked out on
Just kidding.
You do? This did? Oh, wow, what?
Yeah, I know.
I'm the fans.
Okay, stretch break is over. Well done if you did actually move some muscles, not just your beating heart. So, I forget where you were. In Miami, and Annika was in Florida, wasn't it? Was it Florida?
Yeah.
Okay, bit of maths and a bit more chat. So, thermal expansion. Most materials expand as they get hotter. Why do they do that? Why expand if something gets hotter? Yeah.
Is it something to do with the bonds loosening up?
Ooh, yes, it is. But there won't be necessarily, we're not looking at a chemical reaction between the two. They are loosening, but if you imagine that the particles inside, imagine you're a bunch of particles and you've got a really miserable cold lesson and you're all just sat there doing nothing. But then you get a little bit more active. The atmosphere warms up a little bit. Maybe you're allowed to chat to your partner. You actually begin to move around a little bit more. So the particles, as they get hotter, they move more. They don't actually maybe leave their place, but they oscillate with a bigger amplitude. So they move from side to side a bit more. And when you've got a whole lot of billions and billions and billions of them doing it, then you get an increase in length or volume, length, area, and volume. So it's to do with the fact that the particles are oscillating more. Yeah.
But why not in width? Why only in length?
They do both. They do it in three. Yeah. So length, area, and thus volume. So in every direction. Yeah.
Does this have like a same kind of like a thermal expansion? Like for example, when like ice is melting, like the molecules start moving more, and when it like condenses, when water condenses, they move out.
It's also why you, if you have 1 gram of gold, its volume as a solid is smaller than 1 gram of gold as a liquid, and 1 gram of gold as a gas will occupy whatever space it's allowed to. Yeah.
What does gold look like as a gas?
It's always one who asks the really wacky, difficult questions. It might even be genetic, because your sister was really good at it as well. Sorry to mention your sister again. What does gold look like as a gas? Wow.
I've never heard of gold being a gas. Neither.
It's a possibility. You just heat it up. But you can make a gas out of any element if you heat it up enough. You're saying, will it look golden? Will it have a colour?
I'm just asking what it
Yeah.
would look like.
I think it would be colourless, to be honest. Because what makes gold look golden and what metals look a particular way, or gives an element a particular colour, is the way the outer shell electrons are arranged, and in a solid metal structure it's different to being in a gas. So for instance, solid dry ice, solid carbon dioxide, is a white solid, but as a gas, it's a white gas.
Isn't it transparent?
Yes, it is. As it vaporizes, it's transparent. When it comes out, it's a solid powder, isn't it? Yeah. Very good question. Hydrogen is a colourless gas, but you can freeze hydrogen down to its freezing point, and it can become a metal, so it can look metallic. Okay, moving on. Most materials expand as it gets hotter. This is because the average distance between particles inside the material increases because the particles vibrate more. At absolute zero Kelvin, they don't vibrate at all. So there's no thermal energy. Wait. Who said wait? I'm not moving further from that at the moment. I'm pausing. I wondered what you want me to wait for. Thinking. Okay. Ella.
So that like particles in all like objects like move some like even a little bit, if they're not like at zero.
Yes. Okay. So, the expansion is measured using the coefficient of linear expansion in English. In Finnish, anybody want to guess? Actually, I've missed it out in English. Coefficient of linear thermal expansion. Sorry. So, have I?
No, I didn't.
Oh, okay. Why on earth am I bothering with all this stuff? I'm bothering with all this stuff because you've got the IB entrance test coming up. You've got physics becoming a lot more mathematical next year. I know, it's a bummer. But to really get on with physics, you've got to do the maths. And I'm just trying to make it a little bit more technical. So I believe coefficient, which is, you must have met that word in maths, that is keroin, yeah. And this means the length. There is a volume expansion coefficient, but we don't usually bother with that. It's a similar sort of principle. Okay, the formula, which I haven't decided if I'm going to make you learn or not yet, is delta L. You're happy with deltas, are you? Silence. You tolerate deltas. You know what they mean. Yeah, what does it mean?
The change or something.
Yeah, the changing. So this is, I'll write it in words underneath. I'm going to do a capital T there. It's different to what Ilma says. I am really sorry if the sight of that fills you with absolute horror.
Yeah, it does. Fish.
Alpha, not fish. I've tried to follow the Finnish system with the dots for multiply. I think it's Cheyenne who absolutely hates it. If you want to write it with X's, please do. We are multilingual in this class, so you can do that. Or you could be really big and nerdy and grown up and do that. They are the same. Choose your poison. Whichever one you want. What did you use in the US? X.
Yeah.
X.
Division, it's not like just dots, it's lines.
There's a line.
Oh, Finnish division. I can't do. I don't get that.
I don't get it either.
I'm sorry. I don't. I finished teacher's marking. I'm sorry. I don't mean to be rude, but what does that mean?
Yeah, it looks like percent.
Oh, yeah. It's like 4% on the. Like you got 4% of the.
Is that where it comes from?
That doesn't make any sense.
And wrong?
You're
Is
wrong.
that?
But it didn't just like be like wrong like that.
Is that where it comes from?
I don't know. I always thought that way.
Yeah, it's B for that. Yeah.
4 points.
Oh. But that,
But the percentage is fine that you like, so the difference way.
it's that.
Oh, no, I
No.
think it's tilted the opposite way as a percentage.
Brigitte?
Thank you so much. It is the mark.
Only half a point. The minus mark is like 0 point, and then the plus mark is like 1 point.
Wow. Okay. Yeah, I must admit, I've never changed to finish marking. Okay. So, delta L, you don't have to write it, the formula again. I'm just writing it again because you may have written it at different times. That is the change in length. Now, if your length unit is in meters, your change in length will be in meters. If your length unit is in kilometers, it will be in kilometers. If your length unit is in boron kursema, it will be in boron kursema. That is a real unit. Boron kursema. Have you never heard it?
Yeah.
Yeah, you lot have. It's a brilliant unit.
You talked about like last year or something.
Yeah.
Okay, I'm hearing something different. What is this again?
This is the teacher who can't resist being distracted. It's real. Yes. It's an old measuring distance, the distance between reindeer peas. It's not a fixed distance. It's true. It's on Wikipedia. It's true. Whatever your distance measurement is in, then it could be in inches or whatever. It will be change in length will be in that length. Okay. Alpha is this coefficient. And I can't be bothered to write it out again. L is the length, and then delta T, change in temperature. Bless you. Spot the non-things. Okay, you have to look up that coefficient. You are not expected to remember them. There are far more important things in life that you should remember, not these coefficients.
So is that the coefficient of the same?
Yeah. And so, for instance, e.g., iron, 0.40, and then the unit per degree C. If temperature is in degrees C. So it could be per Kelvin. You will not find it per Fahrenheit in my universe, but it could be. And it's actually it's a percentage, really, of how much a distance or a length changes for each change of degrees Celsius. Now, each different material has got a different coefficient. So, in fact, when you get into the sauna, and you all have amazing Sissel, so your sauna is at what? 85 Celsius? Yeah. You then, because you have a huge degree of Sissel, dash outside and jump in the ice at 0 degrees Celsius. Your bone will contract. Your skin will contract. Your muscles will contract. Gentlemen, certain bits will really contract. But in fact, even though different materials in your body are contracting at different rates, your body can accommodate that because it's soft and bits fit together. On average, yeah, you jump in the sauna and you do shrink. All of you.
Wow.
Because it's cooler. Yeah. On a hot day, you are taller than on a colder day.
That's why the dry and they get crunchy together.
No, sadly not, because you also have evaporation issues there, things like that. Good try, though. Good try. Why? Okay, we'll talk about dry lips in a minute. If you continually did that to the expansion, contraction, if you continually did that to other compound objects, not just bone and muscle, but plastic, metal, then you might get problems. I am not a very good practical physicist. I'm good at the theory. So, having made what I thought was the perfect cat flap, which is at the end of a wooden tunnel, so there's no major heat loss from the house, but the end of the flap, I decided it had to be covered. So I had plastic material so the cats could see where they had to go, and I drilled little holes in, and I put metal screws in there. And on the first day, it was -25. The plastic expansion and the metal expansion were completely different. And the bolt on the metal had contracted so much, it had shattered the plastic and the door fell off. So when you're using plastics and metals, actually you get really big problems in cold temperatures. Okay, I am going to make you do a calculation then. Let's stick with iron, just because you've got iron. The iron lift cable. Yeah. In Jeddah is 40 meters long. By how much did its length change when the temperature dropped to -25 degrees Celsius from, what was the maximum it got to this holiday? 3.
Oh, it was what's it called? -31.
Yeah.
Yeah.
What was the warmest it was?
2.
I'm going to lie a bit because it makes the numbers easier. And I don't think you'll object to a lie there. Plus
White
5. Okay, let's see how many of you can do it. No calculators. Feel the pain. No pain, no gain. No ibuprofen. Why am I being such a sadist? Because in the IB entrance exam, you can't use a calculator. I might not be right. I haven't checked it on the calculator. You know what the old brain's like at the moment. Have you got 0.0144 meters?
Hey.
Okay. I put that problem pretty high up the list of horrible problems in maths because of the zeros. If you're good with standard form, like writing 1.2 times 10 to the minus 5, if you're good with that, it's a lot easier. Okay, now if I was wanting to give you marks for that problem in a test, you would not get full marks if you just wrote down the answer, obviously. Formula, 1 mark. So you should write in the formula. Correct substitution. I'm sure Anna and Umpty have told you this many, many times. Delta L we want, alpha, the original length 40, and the change in temperature 30. That's why I wanted 5, make the numbers easier. Change in temperature. You then do the maths for it. Answer and unit. And that would probably be 5 marks. Okay, I know, horrible. Now, I didn't see a single one of you reach for your calculators because I told you you couldn't. I couldn't quite see the back row, but I believe you didn't. So, well done if you did that. No, I know. But most of you tried it and you weren't scared and you survived the experience. Yeah. Now, Annika, I will remind me about cracked lips next week, and I'll try and explain that one. More examples of your physics teacher cannot do practical physics. A few years ago, I went up to Harper London, came back with a load of cans of Coke. Yeah. To give to a friend. What did I do? It's middle of winter. I left them outside because they were out. Only they didn't bring them into the house when they got in, so they left them overnight. As my friend said, what do you actually do for a living? Physics teacher. Half of them had broken. So as they had frozen, they had cracked. Not good. I was not happy.
Was it just like bumpy or what was it for? Didn't matter.
No. But that I actually had thought mistakenly that there was enough of an air gap in ordinary Coca-Cola for the expansion when water freezes to not matter. And actually there wasn't. Now I said here most materials expand as they get hotter. There's one very important material that is a little bit weird, and that is water. Liquid water doesn't have its minimum density, its most compact contracted form, at 0 degrees Celsius. It has it at 4 degrees Celsius. And for that reason, ice actually floats. Usually you'd expect solid to sink in its liquid because it's got a higher density. So if you had 1 gram of gold, it is, as a solid, it's more dense than 1 gram of gold as a liquid. Water is different. Thank goodness. What if ice sank? Yeah, why? Why, oh my God?
Wouldn't the water rise?
Yeah. You couldn't skate on a lake. And most importantly, yeah, you'd have ice at the bottom. Yeah, where would the fish live? If you didn't have ice forming on the surface, none of the living stuff underneath could cope. Yeah, there would be some sort of balance because actually in a very, very deep ocean, it's warmer at the bottom because you're closer to the center of the earth, volcanic stuff, blah, 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 blah. The deeper down you dig, the warmer it is. But if ice didn't flow, and we've got our Earth's temperature hovering around 0 in a lot of areas, then life as we know it would not exist. It's kind of mind-blowing.
I remember at the time I went to the Bonnie Bridge.
Yes, it is. When you go ice swimming, yeah, you've got the ice effectively covering over the water, insulating it, keeping it warmer. If you then swim in the ice, it's warmer than the air. You're in the warmest part of the outdoor environment if you are in the water rather than on the ice. Think of that with a bit of comfort next time you go ice swimming.
Yeah, like.
Do you still have to go ice swimming in PE?
No, we've never done that.
Boys, do you have to go ice swimming in PE?
No.
Oh, 5 years ago with a different PE teacher, you did used to have to. Was it Yana? Yeah, he taught the boys how ice swimming. Yeah.
And they had to do it.
He assessed them on it.
Oh my God. Was it like how long you survive in the water?
No, but you just had to have done it. Yeah, everybody used to go out to Sweden to do their ice swimming. Oh, it's no longer done. By your packing up, are you indicating to me that it's the end of the lesson? Okay, homework, read through your notes, make sure you understand it. I'm sure nobody will.